All right, so the next thing we want to talk about is metabolic reactions and energy transformations. As we said before, all living organisms maintain their structure and function through chemical reactions. And metabolism is just going to be the sum total of all the chemical reactions that occur inside the cell. Now, there's a couple of terms that we want to define here before we go any further. First is reactants. Reactants are going to be the substances that participate in a reaction. Products are going to be the end result of that chemical reaction. So, unfortunately, I don't have a whiteboard in front of me. This is normally the part of my lecture where I go into a chalk talk. So I will just spend a little bit of time with this. Make sure you join us for our discussion group in the evening, and we will go over chemical reactions. But just know that in a chemical reaction, what we have on the left side of the arrow is going to be the reactants. On the right side is the products. So in the example where we are making, let's say we're making glucose. We need carbon dioxide plus water to equal glucose. Reactants would be the carbon dioxide and water. The products would be the glucose. So the reactants are what goes in, products are what comes out. Not all reactions occur spontaneously. Some are going to require the input of energy in order to occur. For example, the production of glucose from carbon dioxide and water is not going to happen on its own. Remember, we already talked about that's going from an area of less organization to an area of more organization. It's like walking into your room and realizing it's super messy and just hoping that one day it's going to clean itself. It's not going to happen. Your room is not going to suddenly become more organized just because you sit around and wait for a million years. It's never going to happen. The only way to get that room cleaned up is to input energy, to expend the energy to clean it up. So here's the interesting thing. All reactions are going to either require the input of energy or release energy during their process. So free energy is going to be the term that scientists use to describe the energy that is available to do work. Now, in some reactions, there's going to be more energy available to do work after the reaction is over. Sometimes there's going to be more energy available to do work before the reaction starts. And we are going to define these two types of reactions called endergonic and exergonic. Exergonic reactions occur spontaneously and result in the release of energy. The products have less free energy than their reactants, so we're releasing energy into the environment. Great example of this would be breaking down glucose into carbon dioxide and water. So we have glucose is our reactant, our products are carbon dioxide and water. We're going from a high energy state to a low energy state. The products have less energy than the initial reactants. So energy was given off, released into the environment during this reaction. In most cases, reaction is going to be given off in the form of ATP. And we're going to talk about that a little bit later on. Endergonic reactions, on the other hand, exergonic reactions are going to occur spontaneously. Endergonic reactions, on the other hand, do not occur spontaneously. They require the input of energy to occur, and that energy is going to most often come in the form of ATP. So they are non-spontaneous. Again, endergonic reactions would be like sitting around waiting for your room to spontaneously clean itself. Not going to happen. You're going to have to put energy in order to drive that reaction forward. Again, photosynthesis is a great example of an endergonic reaction. You can put a leaf, you can give a leaf all the carbon dioxide and all of the water that you want, but unless you also give that leaf or your plant solar energy, that plant is not going to grow. It's never going to produce carbon dioxide if it doesn't have an input of energy from some source like the sun. So like I said, a lot of the energy that we're going to use comes from the form of ATP or is converted into the form of ATP. So we're going to spend a little bit of time talking about ATP. ATP is adenosine triphosphate. It's the most common currency of energy in the cell. When cells require energy to drive chemical reactions forward, they use it in the form of ATP. And it's important to note that energy is not going to be stored in vast quantities of ATP. This is not stable. ATP is not stored by the cells. We don't hold on to it. Personally, you can think of this however you would like. but it's not for long-term storage. You're going to make it when you need it, and then you're going to use it up. Ooh, I like to think of it as cash. Personally, I don't hold on to cash. If I ever need cash, go to an ATM, get cash, spend the cash, go on with my day. If I want to store cash, if I want to store money, if I want to store currency, I store it in a bank account. I don't store it in the form of cash. To me, that's unstable. I'm irresponsible with cash. Let's be honest. I'm very responsible with my bank account. I'm not responsible with cash. For me, cash is not a safe way to store energy. It can be lost. It can be stolen. It can be spent. So if I want to store currency, if I want to store money, I don't store it in the form of cash. Same with ATP. We do not store it in the form of cash. Another great example of this, cake. I do not store cake in the form of cake. Cake is not stable, does not last long in my house. If I want to store flour and sugar and butter and eggs, I leave them in their raw components. If I want cake, I will put them together, I will make the cake, I will eat the cake. I do not store cake in the house, or I do not store eggs and flour in the form of cake in the house. That's not a great way to store energy. It's not a great way to store cake. Because it just gets eaten. So anyway, ATP, we make it as soon as we need it. We use it as soon as we have it. It's not really great storage. I know we said it's short-term energy storage. It is, but it's very, very temporary. It's more a transition state for energy. We convert glucose to ATP, we use ATP. Because we can't use glucose. Glucose is not, it's a very large molecule. We can't break it down for metabolic reactions. So we store it as glucose. We break that glucose down to turn it to ATP, and then we use our ATP. So ATP is not going to be stored by the cells. When we need it, we generate it. And it's constantly being generated from adenosine diphosphate. Now, if any of you know your Greek and Latin roots and prefixes and suffixes, do you know what the tri stands for in triphosphate? Tri stands for 3. Adenosine triphosphate, if you remember when we talked about the structure of ATP, adenosine, it has 3 phosphate groups built onto the end. All of the energy is going to be stored in that final bond between the second and the third phosphate group. When we break ATP to release energy, we break it down into adenosine diphosphate. Di meaning 2. We are releasing one of those phosphate groups. So the D in ADP stands for adenosine diphosphate, di meaning 2. This is going to be the ATP cycle. I know it's a lot of words, so we're going to take a moment to look at that. This cycle is going to be powered by the breakdown of glucose and other biomolecules for cellular respirations. However, as we just learned, in accordance with the second law of thermodynamics, this process itself isn't terribly efficient. Only about 39% of free energy stored in chemical bonds in glucose get transferred to ATP. The rest is going to be lost in heat. This is why we give off so much heat. This is why muscles give off so much heat. This is why you get hot when you work out. When you're doing a lot of these conversions from glucose into ATP, you're going to be giving off massive amounts of heat. This is one of the reasons that our bodies shiver when we are cold, because if we undergo those muscle contractions, if our muscles start contracting, they're going to be breaking down glucose into ATP. At that point, we are literally just moving to keep ourselves warm, because this is how our bodies produce heat and help maintain homeostasis. So there are a lot of advantages to using ATP as our primary energy carrier in living systems. ATP can be used in a lot of different types of reactions. It can also be easily coupled with endergonic reactions to maximize efficiency and reduce energy loss. So here we have a molecule of ATP. ATP, let's take a quick moment. Can anybody tell me ATP, is that a carbohydrate, lipid, protein, or nucleic acid? And I'm actually going to leave that up to you, but you should be able to answer that question. If you're not able to answer that question, please go back to chapter 3 and review those 4 categories of biomolecules and figure out where ATP falls into those biomolecules. Is it a carbohydrate, lipid, protein, or nucleic acid? Like I said before, here's the structure. We have an adenosine, so we have an adenine bound to a ribose, bound to 3 ATP, or 3 phosphate molecules. ATP is considered a high energy molecule because these 3 phosphate groups repel each other. They do not like to be together. They don't like to be this close, thus they form a really unstable bond when all 3 are in close proximity to each other. This 3rd phosphate group can break off very easily, and when it does, it releases a bunch of energy. There's a whole lot of energy stored in that bond. So the breaking off of that 3rd ATP molecule is considered an exergonic reaction. The hydrolysis of ATP, remember we use hydrolysis to break covalent bonds apart, whether we are talking about carbohydrates, lipids, proteins, nucleic acids, we're going to break all of those covalent bonds with hydrolysis. The hydrolysis of ATP releases the previously stored energy. It allows a change in free energy to do work and drive other processes. Has a negative delta G. You don't need to worry about delta G. You're going to see that if you take other chemistry courses. It just means that we have a negative free energy, or there's going to be energy released in this process. We don't have to put energy in. Energy is released in this process. And we can use that energy for nerve conduction, muscle contraction, and we can use that wherever we need to. Now, ADP, what we have just formed, we've taken an adenosine triphosphate, we've broken one of those phosphate heads, and what we have now is adenosine diphosphate and a phosphate group. All we've done is just snapped that phosphate group off. Now, ADP is going to be much more stable, but it has a lower potential energy than ATP. There's less energy stored in these chemical bonds now that we have broken off this high energy bond. So what we need to do is, if we need more ATP inside the body, once we use up the energy given off, we need more energy, more ATP, we're going to have to undergo an endergonic reaction to glue ADP to that phosphate group. We need to reattach that phosphate group to ATP. So we're going to create ATP from ADP. It's going to require an input of energy from other sources. This is going to have a positive delta G. So a great example of this would be carbohydrate synthesis. We're going to synthesize carbohydrates, and we're going to, carbohydrate synthesis, breaking down carbohydrates. When we break down glucose into its smaller molecules, we're going to release a bunch of energy, and that energy can be used to make ATP out of ADP and P. Then when we need that ATP, we're going to spend it. We're going to break that phosphate group. We're going to release that energy. When we need more ATP, we're going to take carbohydrates like glucose, we're going to break them down. The energy we get from breaking glucose down can be used to glue that P back onto ADP and form ATP again. So ATP, it's going to be composed of adenine ribose. Together they make adenosine and 3 phosphate groups. The next thing I want to talk about is coupled reactions, because coupled reactions is how we use the energy released by an exergonic reaction to capture it in ATP. In other words, when we break glucose down into carbon dioxide and water, we're going to release energy, and we're going to store that energy temporarily in ATP. The great thing about ATP is that ATP can be transferred throughout the whole cell. ATP can go wherever it needs to go and then be spent however it needs to be spent. So we want to convert our stored chemical energy from glucose into ATP. ATP can then be used to drive an endergonic reaction, reactions that require an input of energy, like transporting molecules against their concentration gradient. That's going to require energy in the form of ATP. So here's a great example of a coupled reaction using ATP to drive reactions forward. So here we have... Actually, you know what? I'm going to set this aside. I would like to encourage you to send me some extra credit videos of actin and myosin filaments and how ATP is coupled to that to drive those reactions forward. So yes, this would be a great opportunity for you to send me an extra credit tutorial video. Find yourself a video that explains coupled reactions, actin and myosin filaments. Watch the video and then send it to me and explain what you've learned from it. So yeah, we're going to skip over this slide and I'm going to let you guys look into that a little bit on your own. And then if you have any questions, please let me know and we'll talk about it in our discussion time.